Hello, welcome to Electronics Education. This is Vincent Chang. Today we're going to start a new series on frequency response, which is one of the most challenging topic for either college students or engineer. So I want to make sure you watch the lecture video. You can lay a strong foundation in this area, frequency response. Intro to frequency response. sDomain, S means the complex frequency. So sDomain represents the complex frequency domain. So sDomain and the transfer function. sDomain and the transfer function. Let's start with the transfer function. So the H as function of S represent a transfer function of a circuit system. The transfer function of the circuit system. And the output signal in sDomain is VO on the right hand side as a function of S. On the left hand side is the input signal, input voltage signal as a function of S. The transfer function H of S is defined as the output signal VO divided by the input voltage VI of S. VO divided by VI. Again, the S is the complex frequency. So complex frequency equals J, imaginary J times omega. So omega represent, you want to take note, physical frequency. So again, S represent the complex frequency and omega represent the physical frequency. So let me give you a general form of the transfer function. It's the numerator polynomial and denominator polynomial. All right. So for the numerator part, the polynomial, the highest order is the m. For the denominator polynomial, the highest order is the n. And then we can reduce to this a simple form. And then you find some roots in the numerator and the denominator. For the denominator, for the roots of the denominator, it's called pole. So P1 is the first pole and P2 is the second pole. So there are m poles from the denominator of the system. In the numerator, the Z1, Z2 to Zm is called 0. So Z1 is the first 0, and Z2 is the second 0. So this is the definition for pole and the 0. Pole and the 0. So pole represent the root of the denominator polynomial. And the 0 is the roots for the numerator polynomial. All right? Complex transfer function. So now the transfer function is a complex number. It's the complex. So when you send in a signal with a frequency spectrum shown on the left-hand side of the slide. So voltage, the vertical is the voltage. The strength, you can think about the strength of a signal, all right? And then the horizontal is the omega. So it's the signal frequency spectrum. When it comes to the high frequency part, the signal strength goes down, all right? So it's the signal frequency spectrum. So for a signal comes in, enter into the system with a transfer function H of J omega is the complex transfer function. And then two things were changed. Number one, the magnitude of the signal will be changed, right? So think about the basic concept of the math. So how you define a complex number? How you define, what's the physical meaning? Let me ask you this. What's the physical meaning of a complex number? you can put down the 1 plus J2, right? So what's the physical meaning of this? The first one is the magnitude, right? So 1 square plus 2 square and take a square root. So square root of phi is the magnitude of the complex number. The magnitude of the complex number. And then the second part of this complex number, the physical meaning is the phase. So the phase is the arctangent 2. 2 divided by 1. The imaginary part divided by the real part, right? So magnitude and the phase. So same thing in the electronic system. So when the electronic signal comes in through, going through a system with a complex transfer function, two things will change. Number one, magnitude will change. The signal strength will change. And also, there will be a phase leading or delay. So phase will be changed. It's called phase response. So in the upcoming lecture, I'm going to go deeper to teach you how to investigate a magnitude response and the phase response. So let's start with the sDomain analysis, the complex frequency domain analysis. So we use a term called impedance from a circuit theory. So in the circuit theory, there's the terminology called impedance, the general impedance Z, denoted by the Z. So what is Z? So usually you can think about the passive component, right? The first one, the resistor. Okay? So you just copy. If it's the resistor, a real number, the resistor 1 kilo ohm, 2 kilo ohm, so the impedance of the resistor is the resistance itself. The value of the impedance for a resistor is the value of the resistor. All right? So just duplicate, just copy. But for capacitance, a little bit tricky. So it's the 1 over SC. It's the impedance equals the 1 over SC. So what is S? Look at the slide. It's the J omega. All right? So J omega C. So it's the purely for the capacitor in the S-domain analysis is the purely imaginary number. So same thing with inductor. So if it's the inductor, then the impedance is SL. It's the J omega L. And then you convert from the RCL to a term called impedance. It's the general impedance, and you try to derive the transfer function based on the circuit theory. Say the Ohm's law, Kirchhoff voltage law, or Kirchhoff current law. And then once you get the transfer function in terms of S, then you plug in, you replace S with J omega. Then you get a complex transfer function. And then for a complex, same thing you learn from the math. All right? So magnitude response, and then you investigate a phase response. All right? So this is the big concept. The whole concept of the S-domain analysis. Let me show you one example, right? It's called single time constant circuit. A single time constant circuit, right? RC, the single time constant RC circuit, the VI and the VO. VI and the VO. The V is lowercase. But usually in the S-domain, okay, I try to differentiate the variable when it comes to a complex domain analysis. We use the capital V. So capital V as function of S and capital VO, the capital V, represent the output voltage in the S-domain. All right? And then, so how to analyze this? First step, you replace the RLC with a general impedance. Replace RLC with general impedance Z. So R becomes the Z1 and C becomes what? C becomes the Z2. So what is Z1? I just told you that the Z1 for the resistor you just copy. So Z1 is actually R itself. The value doesn't change. But for the capacitor, it's going to be a 1 over SC. 1 over SC. And then you try to derive the transfer function. You just think about the Z as if you do a circuit analysis for a current, voltage, and the resistor. So same thing here. In other words, for the current in a series loop, the current going through the Z1, Z2 are the same, right? So this reminds you the voltage divider rule. So the VO divided by VI is going to be Z2. Same thing with the voltage divider rule. So Z2 divided by Z1 plus Z2. And then you plug in, you do a little bit math, then you can get this. 1 over 1 plus SRC. And then the inverse of a time constant, the RC. What's the dimension for R times C? It's time. So it's called time constant. So RC, again, the dimension of R times C is time. All right? So the inverse of time is frequency. And the frequency happens in the denominator. So this frequency is called pole frequency. So it's called pole frequency. So the pole frequency is the 1 over RC. All right? So this is the single pole transfer function. A single time constant circuit, a single pole transfer function. So we almost come to the end of this lecture. Let me just give you a takeaway of this lecture. Let's start with the Z, the impedance. And then here's the rule. R, 1 over C, and then SL for resistor, capacitor, and the inductor respectively. And then you try to derive the transfer function in the S domain. The transfer function derivation in the S domain. And then you replace S by J omega. J omega. Omega represents the physical frequency. And then the complex transfer function reveals. And then you dive in, you split two parts. The first part is the magnitude frequency response. The second part is the phase frequency response. So in an upcoming lecture, I'm going to go deeper to investigate the magnitude response as well as the phase response. So this is the end of this lecture video. Thanks for watching.